It's a new day and a new pattern for us to consider. The ninth pattern we're considering in this series with educative.io, and it's the modified binary search. There's the intro to it. It's an extension of traditional binary search of the traditional binary search algorithm, and can be applied to a wide range of problems. So we're going to recap classic binary search. So it's an efficient search algorithm for finding a target value in sorted arrays or sorted lists that support direct addressing, also known as random access. It follows a divide and conquer approach, significantly reducing the search space with each iteration. It uses 3 indices: start, end, middle, and proceeds as follows. Then they go ahead and start giving us all of this lingo. It's a huge wall of text. So I'm just gonna use this diagram right here to explain. It pretty much explains everything they've been saying. So you need 3 indices: the start, the middle, and the end. So you calculate the middle by taking the floor of the start plus end divided by 2. So it lands you in the middle. That's where the middle pointer is. So you need these 3 pointers. And let's say our target is 98. We're trying to find 98 in this list, and the list is sorted. These are the conditions that you need before this classic binary search algorithm would apply. So we check it. Because 98 is less than the target, we move the start to the thing right after the middle. Over here, 75. Then we update the middle by taking the start plus the end divided by 2, the floor of the start and the end divided by 2. Then the elements at the middle is equal to the target value, so the algorithm ends here. That's it. That's all there is to it. That's what this entire block of text is trying to say. So now we have the modified binary search, which is what we're dealing with for the next 1 week, give or take. I think, well, how many problems? 7 problems, so 7 videos. And this builds upon this basic search algorithm, and it involves adapting the traditional search approach by applying certain conditions or transformations. And we can solve more complex problems this way. These are some common variations of the binary search pattern. You want to search on a modified array. So sometimes the array may be modified in a certain way, which affects the search process. For example, the array might be sorted and then rotated around some unknown pivot. Alternatively, some elements in a sorted array might be modified based on a specific condition. To handle such scenarios, you modify the basic technique to detect anomalies in the sorted order. And another variation is with multiple conditions, binary search with multiple conditions. When searching for a target satisfying multiple conditions, a modified binary search can be used. It involves adapting the comparison logic with the binary search to accommodate multiple conditions. Okay, so if you want to find a target range rather than a single target, or find the leftmost or rightmost occurrence of a target value. And we have some more examples here. This says find the first and last position of an element in a sorted array. So we have, so in this array, for example, we want to find when 9 occurs first and when the last time it occurs, because it occurs multiple times. And again, the array is sorted. So you use binary search 2 times, one to find the first time and another to find the second time. And so in this case, if the middle index, so we start out the way we started out before with a start, middle, and end. You check if the middle index is equal to the start index, right? If we've done our divisions to the point where the middle is equal to the start, then we have the first occurrence. Otherwise, we check if the element to the left of the middle index is not equal to the target value. So if this condition is satisfied, the middle index is at the first occurrence. So you're at the middle, your pointer is at the middle, you check, oh, is the left equal to what is at the middle? Is the left 9, just like 9? This is 9. If it is not 9, then you have found the first occurrence of 9. If it isn't, then you have to do binary search from the left backwards till you find what you're looking for, the first occurrence you're looking for. And then for the last occurrence, you check the middle again. If it's equal to the middle and the end coincide, then we have the last occurrence. Otherwise, check if the element to the right. This time we're checking to the right. For the first occurrence, we're checking to the left. For the last occurrence, we're checking to the right. And if that is satisfied, if we check to the right and what's at the right is not equal to what's at the middle index, then we know we're at the last occurrence. Otherwise, we keep searching the right side of the array. It's another example, integer square root of a number. So if the number is 0 or 1, return the number. What's the integer square root of a number? It's basically math.floor for the root of the number. So let's say the root of a number was 2.5. The integer square root is 2. So if the number is 0 or 1, just return the number. Otherwise, we set the left boundary to 2 and the right boundary to the floor of the number divided by 2, because the square root of a number is always less than half of the number. Or yeah, less than or equal to half of the number. So the right boundary to the floor of the number divided by 2. While the left is less than or equal to the right, we calculate the middle as the floor of the mean of the left and right. That's interesting. So the floor of the mean of left and right, 2 plus 5 is 7. Divided by 2 is 3.5. The floor of that is 3. That's why the middle here is 3. That's what that lingo is saying. And so we keep the square. We now square that, whatever is at the middle, and in a variable called checkback. So 3 squared is 9. If the checkback is equal to the original number, mid represents the integer square root of the number. Oh, okay. So if checkback is equal to what we're looking for 10, right? Mid represents the integer square root of the number. Okay, so we return mid. Otherwise, so in this case, 9 is not equal to 10, I would say. Or is it? Okay. No, it's not, obviously. So if checkback is less than the original number left is set to mid plus 1. If it's less than, okay? C panels 1 and 2. So mid plus 1 is 4. Checkback is 16. Also, if checkback is greater than the original number, right, it's set to mid minus 1. Okay? Finally, our loop ends. Left becomes greater than right. We simply return right. Okay. This is a bit more confusing. So in this case, we're looking for the integer square root of 10, which should be 3, because 3 squared is 9. And it's the closest we can get that is a whole number, like 3 squared. 4 squared is going to give us 16. So this second piece here is saying if you do your left, right, and find the middle, which you get by doing the floor of the mean of left and right, so 2 and 5, the floor of the mean of 2 and 5 is 3. If that is equal to what you're looking for, if 3 squared would have been 10, would just return mid. Otherwise, because 9 is less than 10, 3 squared is less than 10, we move the left to 1 position after our former mid and set the new mid based off of that. So in this case, we have 4 plus 5 is 9, divided by 2 is 4.5, and the floor of that is 4, so mid is also at 4. Then we do another checkback. Checkback is the square root of mid. We get 16. That's what all of this body of text is saying, and you can pause and go over it more. And then we check, since it's bigger, we move the right. So that's what you do when it's smaller, right? You move the left. When it's bigger, you move the right to 1 minus the new mid. So the right is going to be at 3. And whenever your left comes after right, you terminate the checks. You stop checking. And you return whatever right is pointing to, which it will be the integer square root of 10, which in this case is 3, as you can see. All right, so does your problem match this pattern? It does if you need to find a target value, first or last occurrence in a sorted array or a sorted list that supports direct accessing. So if the list is sorted, you won't need a target value or first or last occurrence in a sorted array, then this pattern works. You can use it when segments, also use it when segments of an input array are sorted. even if the whole list does not at first sight seem to be sorted. For example, you can use this technique to find a target in a sorted array that's been rotated around an arbitrary pivot and know if these conditions are fulfilled. If there's no direct accessing for the input data structure, you can't use this method. If the data to search is not sorted according to criteria relevant to the search. For example, if you're looking for a particular date in a list of dates, but the lists are sorted alphabetically, not chronologically, then we cannot use this pattern. And if the solution does not require us to find a particular value or range of values, then this is not our problem. So real world problems that use this pattern. We have a dictionary. So words, they're sorted alphabetically. You can use classic binary search to find a required word quickly. And if you want to find all the words in a dictionary that share a common prefix, you can modify the comparison operation used in a classic binary search algorithm. Debugging with minimal support. So let's say we have a code script consisting of n lines, and there's a bug somewhere in the script. Binary search is performed to find the bug by dividing the code base on line numbers. For example, if the code does not run for the first n over 2 lines, we divide it again and check if it runs for the first n over 4 lines and so on till we land on the line that is bad for the code. Student documents. So you have some documents sorted by scores on a test. Find all students who scored between 40 and 55. You would use this pattern to do it most effectively. All right, strategy time. We're going to match these problems here with whether they use this pattern or some other pattern. Detect a cycle in a graph is a fast and slow pointer. Is it fast and slow? Yeah, fast and slow pointer problem. So some other pattern, check if a number is the majority in a sorted array. Well, the array is sorted. If it's the majority, I'm gonna just guess and say this, could be wrong. Peak element in an array where the peak element is the one that's strictly greater than its immediate left and right in neighbors. Okay? Assume that adjacent elements in the array can never be equal. I'm gonna just guess and say this. I'm not sure exactly why. Shift all zeros in an array to the right. How do you shift all zeros in an array to the right? I'm gonna just say some other pattern. Show me what's up. Oh, I got it. How about that? See, iterate through the array in this case. Identify the zeros. Move to zero while maintaining the order of the elements. A different approach, such as 2 pointers, would be more suitable. Yada yada yay. Efficiently narrows down the search space. Okay, so this one was a modified binary pattern. By comparing the middle element with its adjacent neighbors, we move to the particular half of the array based on this comparison. The first and last elements can be considered as peaks if they are greater than their only neighbor. I don't really get that, but an image would have been nice. So check if a number is majority element in a sorted array. Find the index of the first occurrence of the given number, then calculate if that number exists more than n over 2 times in the array. Okay, this makes sense. Cycle in the graph, we've seen that before. So random search for specific random condition. So you need depth first search, breadth first search, or like a 2-pointer approach, right? If not, fast and slow pointer approach, and I have videos on that. If you go back to the close to the start of the series, you will find a video on that one. The other one that doesn't really make too much sense to me right now is this one. Narrows the search space by comparing the middle element with its adjacent neighbor. Okay? Neighbors. We move to the particular half of the array based on this comparison. The first and last elements can be considered as peaks if they're greater than their neighbor. Yeah, I don't really get that. But we can go ahead. It's fine. It's not, the goal is not really to understand every single thing, but to have a good understanding of everything. Wow, write that down. See you in the next video. An educative a day can keep unemployment away. A video about it might make you a hit. I remember my poem. Ciao.